Hello and welcome to Precision Stuff. Today we're going to talk about parallelogram flexures. This is an example of a parallelogram flexure. It can displace a fairly large amount in one direction fairly freely, but it's actually fairly stiff out of plane. It's essentially a 1 degree of freedom linear motion system with 5 degrees of constraints. However, you can see it has some interesting parasitic properties. As I push it in this direction, the gap at the bottom starts to increase. It's actually not really moving in a straight line, more like a shallow arc. This is another set of parallelogram flexures, and you can see that it has this very nice S-shaped bending to it. It's not cantilevered, it's definitely moving in that wiggle in plane. However, out of plane, it moves in C-shaped bending. It is cantilevered out of plane. You can even take this further and make double parallelogram flexures, where as this stage moves relative to that fixed base, this intermediate stage moves half as much. This helps take out some of the parasitic errors and gives you more range of motion, otherwise changes some of your stiffnesses. You can even take it to the extremes and make systems that have, two flexural supports and exhibit very large ranges of motion, even if they don't have the traditional parallelogram setup. So what is the parallelogram flexure? I have a bar. That bar has 2 beams. Those beams are on a fixed base. And I take my coordinate system. It moves in X. Y is out of plane. Z is vertical. And if I push on this with a force F, I find that it will move a distance delta X. And if I look really carefully, or if I actually zoom out a lot, this bar, it has some thickness to it, and these are rectangular beams. In terms of degrees of freedom, or DOFs, this has 1 degree of freedom. And that is a linear degree of freedom in the X direction. And again, in an idealized world, it also has 5 degrees of constraint. And it has those in all the other directions. And that is y, z, theta x, theta y, theta z. However, we don't live in a perfect world. It has clearly finite stiffness in x. You have to push on it with a force. So you really have, fx equals kx times delta x. However, kx can be small. As small as we want, as small as we need it to be. However, this is the force that your actuator has to push in order to create motion. And likewise, these perfect constraints are not perfect either. If you wanted to push in y, you get an Fy equals Ky times delta y situation. Ky can be made large, or rather, as large as we need it to be, or maybe just several times larger, than Kx. So this is where things start to get not ideal. But this is, again, what we're going for. The next step is to figure out, well, what's the actual range of motion we need of this flexure? And I'm going to say, for this purpose of example, I'm going to choose something that goes plus or minus 10 millimeters of travel. That's something like fun, we can observe it, and it will move a lot. And a rule of thumb here, to help you get started, is that the length of the flexure is probably about 10 to 20 times longer than the deflection. So we're going to call this deflection big delta. So if L, 10 to 20 times, I'm going to say starting point is about 150 millimeters long. Rule of thumb, it depends on the material, depends on the application, and everything else you care about. This is about right. So let's zoom in and look at how do we actually get a flexure to move this far without breaking? How do we choose the geometry? Okay, I just created L from thin air, but what does it really need to be? So let's look closer in detail. This is my beam. It is fixed into the wall, and it exhibits fixed guided beam bending. We'll talk about that in a second. It has a length, a width, and a thickness. So looking at the side, in the deflected state, it doesn't just go down cantilever. It exhibits this S-shaped bending. You probably remember your cantilevered beams, which tend to do something like this. Not only do they exhibit a delta deflection down, they also exhibit an angular deflection theta. In fixed guided, we just get a deflection delta. How do we make that happen? Well, in a cantilever, you're putting in a force F, and you're getting out both a displacement and a theta. If we put in a force F and we put in a torque, FL over 2, we can actually basically use the torque to bend the beam back up in angular and keep just a pure linear translation output. So what does this look like from a stress analysis standpoint? So let us do the shear and moment diagram. The shear diagram is not that interesting. Basically, that force F has to be carried by every single part of the beam, but beams that are long tend not to die in shear. Not a big deal. The moment diagram is a little bit more interesting. Essentially, in the cantilevered beam world, you have a peak moment at the root, decreases towards the tip. You're slowly just gaining moment over time. We actually have an applied torque at the tip, so we have to actually immediately jump up to the full moment, and then by symmetry, it should be the same on the other side. This shape is obviously symmetrical. And you end up with a peak moment of FL over 2 and minus FL over 2. Notice that there's not really much going on in the center. There's no moment, there's no stress. And if you remember, M equals EIK, it's a pretty meek equation, K meaning 1 over R, radius of curvature. If there's no moment, there's no radius of curvature, basically meaning the beam is straight. And that is obviously like the deflection point right there. And it looks like the tip of a cantilevered beam where there's also no moment. So this checks out. The fun thing is you can actually use this to your advantage. If there's no moment here, it's not really playing a role in terms of the stress in this beam, but it actually is playing a role in the stiffness of everything else. So what some people will do is they will reinforce the mid-region of their beams, and they'll add a lot of material there because they can make it stiffer against buckling, they can make stiffer out of plane, more resistant to buckling, without really affecting the stiffness in the primary direction of travel or the stress in the primary direction of travel. Okay, but we still need to figure out how to size this beam for this range of motion without failure. So we know that the stress in the root of the beam is equal to my over I, and we can plug and chug in this setup and with a length, width, and thickness, and we get the sigma, the stress, is 3 times F times L over WT squared. This is actually not that useful. I don't really care about the stress as a function of force. I care about stress as a function of displacement in the beam. So how do I get that? Well, I actually need to pull out the beam stiffness to do this. So I'm going to go to Kx. Basically, the force it takes to push out a plane is equal to, wait for it, 12 EI over L cubed. And this is Ixx, the second moment of inertia in this kind of bending direction. And if you remember, your cantilever is like a 3 EI. This is actually 4 times as stiff. You can find this in handbooks. You can drive it yourself, whatever makes you happy. You put these two together, plug and chug, you're basically saying, Kx equals F over delta. You're solving for F, putting that in here, and you get out that sigma equals 3 times the Young's modulus times delta times T over L squared. But I don't really care about the stress. I really care about, how does this material fail? Because I can get a really strong piece of steel. The stress is higher, allowable stress is higher, but also so is the modulus. The actual equation that matters here is sigma over E is the yield strain. And the yield strain equals 3 delta T over L squared. This is really what's going on here. Geometrically, we are bending this shape. It requires the material to strain. And we want to keep it in the linear regime, otherwise it'll break and yield and kind of fail over time. So the more we move it, and the thicker it is, the higher the yield strain. If we make the beam longer, the yield strain goes way down. It's easier to bend. Fundamentally, how do we choose this number? Well, we're probably going to make this out of metal if we wanted to have good stiffness in other directions. And it turns out that the yield strain of 7075 T6 is 0.007, or 0.7%. That also happens to be the yield strain of grade 5 titanium. It also happens to be the yield strain of a really good hardened steel, something like 4340 or something. So practically, if you're taking a metal to the limit, you're going to get about 0.7% strain. Plastics go much higher, but their modulus is really low. They tend to be kind of soggy at high temperatures. They don't do that well. They're viscoelastic. And 7075 T6 is a lot cheaper, easier to work with than titanium and hardened steel. So if you just care about deflections, go with aluminum to make your life easier. Why would you want to use titanium or steel? Well, maybe you have an application where the absolute strength must be high, or the absolute stiffness must be high, or you're at high temperature, or you need much better fatigue properties, or weird corrosion concerns. Then you might use some of these other materials. But in general, if you just want a flexure to move a lot, 7075 T6 is a really good place to start. Okay, so now we know what the yield strain is of a material. We still haven't solved for the size of this beam. So let's actually go figure that out. So we'll jump over here and we'll say, well, I'm going to assume that the length is 150 millimeters. And if I plug in 0.7% and I plug in the modulus, and I plug in that, and I know my delta is 10 millimeters, I know that the T has to be less than or equal to 5.2 millimeters. Basically, if my thickness is less than 5.2 millimeters, I can move 10 millimeters without reaching the yield strain in this material. If I go thicker than that, it will start to fail on the edges. Doesn't mean it's going to crack immediately, but I'm starting to put it into its yield condition. I'm going to take a guess and say that the width is about 25 millimeters. That seems like a good aspect ratio to have here. And if I calculate the I of that section, IXX, I'm going to get about 2.9 E minus 10 meters to the fourth. Okay, cool. I still have a lot of combinations of things I can do. This seems like a good cross section, but I actually want to be able to push this flexure by hand. And what I mean push by hand, I mean push it easily by hand. I want to be able to push about 10 pounds, call it 50 newtons, and have it move the full distance. So I know that I need Kx of the entire system to be 50 newtons per 10 millimeters, which is 5,000 Newton per meter. And since there's two of these blades acting in parallel, each of the blades needs to have a Kx equals 2,500 Newton per meter. And we have our stiffness equation out here. And we can solve for IXX, because we know the length already. We know the modulus of aluminum at 69E9 pascals. So what we end up with is an IXX that needs to be about 1E minus 11 meters to the fourth. So here's a problem. I made up these thicknesses and widths that satisfy stress, but the I is 30 times higher than I want it to be, which means it'll be 30 times stiffer in X than I want it to be. So how can I reduce this? This is a common problem in flexures where you choose one thing and then you find out you're off by almost an order of magnitude on some other variable that you care about. So what can we do here? I'm going to, if I need 30x, I'm going to take 2x out of the width and basically knock the width down to 12.5 millimeters. But then I need to take 15x out of the thickness. But in I for a beam, 1/12 WT cubed. The thickness is cubed. So if I want T cubed to change by 15x, the cube root of 15 is about 2.5. So putting that together, I just need to drop my thickness down to 2.1 millimeters and my width down to 12.5, and now I have reduced the I by a factor of 30. My T is still less than 5.2, so I'm fine on the stress criteria. But now when I plug this together, I get an I, again, of about 1E minus 11 meters to the fourth. So now that means I'm good to go on the stiffness criteria. So this is one of those situations where you might have multiple criteria to solve at the same point. It has to be able to move without yielding, it has to have low stiffness in this direction, high stiffness in that direction. Maybe it needs to resist buckling, maybe it needs to do other things. And you're going to play those dimensions across each other, and some of them are going to end up being more important than others. So clearly the stiffness criteria is more demanding than the stress criteria in this application. Cool, let's talk about the other directions. Let's say I'm pushing on this thing in the y direction. What is ky? Well, if I look at it from the side, what's going to happen here when I push out of plane, Fy, is that the whole thing will kind of keel over and move, but it won't go into fixed guided bending. It'll in fact be cantilevered, as I showed earlier. What that looks like is that it kind of droops out of plane, and there's a large angular motion as well. So what is the stiffness of a cantilevered beam? Well, Ky is 3EI YY over L cubed. But I have two of them, so I multiply by 2. That turns into this. I already know my length. I know my IYY. I just swap the W and the T. So this is IXX. IYY is 1/12 TW cubed, much bigger because W is bigger than T. And that is about, let's see, 3.4 e minus 10 meters to the fourth. So the IYY is basically 30 times higher than IXX, just from a geometry standpoint. Putting that together, we get a KY is equal to about 42 kilonewtons per meter. So the whole thing is 5 kilonewtons per meter in X and 42 in Y, so it's about 8x stiffer. Now that's not amazing. It's definitely much stiffer than in X, but it's not that stiff overall. Let's compare it to Z. If I'm pulling in Z, I'm now pulling on the two beams in tension, and that is an awesome thing to do because it's way, way stiffer in tension. So I'm going to take 2 times the stiffness in tension, which is EA over L. The area is just WT. Wow, I have no more cube terms in my top or the bottom. So like this is already going much better. And you end up with something like 24 meganewtons per meter. And it's about 5,000 times stiffer in the z-axis than it is in the x-axis. So this means that if you're going to basically make a motion system, you want to be able to push it in x, but you want all the high loads to be in z. If you have high loads coming in y, you might as well rotate your flexure by 90 degrees so that they end up showing up in z. However, if you're pushing down in z, you're exposing these blades to buckling. So you actually have to do an Euler buckling calc to see, can they support those loads? However, as you deform the system and push it in x, it's pretty easy to push on a column that's straight, but once you've put an eccentricity into the column, the buckling stiffness starts to fall off a cliff. So does the z-axis stiffness. So you start to get into all these interesting parasitics. Like, this is just enough equations to get a system to work, but if you're a precision engineer, you need to go a level deeper and figure out what are all the other things that the system is doing that I don't like. And you'll find that z-axis stiffness varies with x-axis travel. You'll find that buckling stiffness or buckling capability varies with x-axis travel. There's also some pretty severe geometry nonlinearities here, or rather parasitic motions. I'm running out of space, but when you take this and you move it, essentially, if you squint really hard, they kind of look like pivots. These beams are just rotating. And you'll get this forward motion. You also get a parasitic lowering called foreshortening. Foreshortening is like foreshadowing, but for not for tall people. And that is actually an issue. If you have a precision system and you think it's moving in a linear direction, but it's actually moving on this shallow arc, that's a problem. How do you actually calculate this? Well, you can invoke, it's basically a cosine error. So here's your length, and it rotates theta, and it moved over big delta, but it dropped down little delta. And you can go through the trig, and you can find that essentially this little delta is equal to L theta squared over 2, which if you plug and chug is also equal to big delta squared over 2L. So it's nonlinear. So for small motions, you actually have very little foreshortening, but as you move more and more and more, you'll find that you're moving in this shallow arc curve. So how do you account for that? Well, that's where you invoke the double parallelogram. If you have two of these systems that have the same stiffness and move the same amount, one will foreshorten in one direction while the other moves in the other, and it basically counteracts. So by use of symmetry, you can get a system with having basically no foreshortening to first order. Of course, there might be slight defects, slight misalignments, like the thickness of this beam might be slightly different from that one. But essentially, if it was built perfectly, you would have no error. And so you have a lot of these tips and tricks to solve parasitic problems. Eventually, at some point, it becomes less valuable. Like, you end up doing so much work to try to fix some little parasitic problem, you might as well just measure it really well and compensate it in some other way. There's one last issue, which, again, running out of space to describe, but when you push on a parallelogram flexure, you'll find that, we talked about this moment here. There's a moment required to keep that beam from rotating. Those moments go into this upper bar. So if those moments are going into the upper bar, shouldn't that upper bar be like spinning and rotating around? How is it balanced out? Well, there's actually parasitic forces in the legs. This leg has to pull down, and that leg has to push up in order to keep the bar from spinning. So now you have a parasitic z-force in your blade, which gets resisted by the stiffness of the blade in z, which is pretty high, but again, falls off with motion. And that results in small deltas, and essentially this whole bar is actually pivoting, it's actually rotating. So as you're pushing it, not only is it sinking down in a shallow arc, it's actually rotating upwards too. There's multiple parasitic motions. And actually, how do you get rid of that? If you work through the math, you'll find that the parasitic moment is FL/2. So what you can do there is if you push at the halfway point right here, let's say you build a bar that comes down from there, and you push at the halfway point, you can now add another torque that's FL/2 in the other direction. And that means that in static positioning, when you're moving really slowly, all the forces and torques balance out, you'll get a really nice pure motion with no tilting. So if you combine the double parallelogram to get rid of foreshortening, and you push in the center to get rid of this tilt, you can start to work out some of these parasitics. The problem is this only works statically. So the center of stiffness is right here. That's where you should be pressing. But the center of mass of the system might be much higher. So if you're pressing at really high frequency, let's say you have a voice coil driving it, you're no longer putting those forces into the center of mass, which means at high frequency, you're basically creating these high frequency torques around that lever arm that will cause the whole system to rotate. The only way to make this work well at high frequency and at kind of low frequency static is to make the center of mass at the center of the stiffness and drive there. And this is actually done in some really good voice coil actuators. You'll find they have a double parallelogram setup, and then they have the voice coil in the middle, and they have these two little beams. One of them reaches up here, one of them reaches down to the base. And basically that voice coil separates apart. The majority of the mass is in the coil, not the bar. And now the center of mass and the center of stiffness are in the same point, and that's the point of actuation. This is a very, very good design. So I hope this was a useful lesson on the parallelogram flexure. You can go as deep as you want to. You can add as many requirements as you want to. My rule of thumb is that you can make any combination of stiffness, buckling, and stress requirements work as long as your flexure is large enough. Practically, you run into packaging concerns of if your object can only be this big, having a 500 millimeter long flexure might not work, even if it gives you all the things that you want. Thank you for listening to Precision Stuff. If you'd like to learn more about this, I highly recommend this booklet. It's called Precision Point. It is released by JPE. They are a Dutch mechatronics company, and they've compiled a bunch of these very valuable like stiffness, force, deflection, and parasitic equations into one booklet and describe a variety of mechanisms you might want to build, as well as their properties and non-idealities. You can also go to a typical handbook, such as Rourke's formulas for stress and strain. You can learn all your beam bending equations there in terms of stress and stiffness, but it probably won't talk about the parasitic motions as much.